This video will be talking about basic rules of differentiation. Our objectives will be to answer conceptual questions involving rules of differentiation, to find derivatives using the basic rules of differentiation, find higher order derivatives of functions using basic rules of differentiation, simplify algebraic expressions into forms in which basic differentiation rules apply, and use derivatives to find slopes and equations of tangent lines. Let's just go back to an objective from last time that we talked about a little bit, but we're just going to repeat it here. So consider the function y equals f of x. Then we can denote the derivative as y prime, which is the same thing as f prime of x. And this is prime notation. It's one of the shorthand ways, and we do that when we are explicitly differentiating f with respect to the independent variable x that is shown there. Don't use this notation for something that we're going to talk about later with implicit differentiation. We need to be a little bit more exact than that. So if we see y and it's a function of only one variable, say x or t or whatever, it's okay to just put y prime for its derivative because we know we're differentiating with respect to that other variable. If we need to be more precise, which we like to do sometimes, we'll tell you that we're differentiating with respect to a particular variable, like this. And that'll be the same thing to us as saying this. We'll also say y prime is equal to the derivative of f with respect to x, like that, or dy dx, like that. And those are just a little bit more explicit to say the derivative of function f with respect to x, or the derivative of y with respect to x. So these notations here, this one and these two, are differential notation because they're using the differential operator. Notation. Not notion, notation. All right, let's now talk about why we care about these basic rules. So memorizing these rules we're talking about today is much more preferable. It's preferable to using the limit definition every time. The limit definition is there for when you don't know a rule like this and you need to use the definition, which always works. But hopefully you know these rules so you don't have to go back to the limit definition every time unless the problem prompts you to use the definition to answer the question, which will definitely happen because that is an objective of the course, to make sure you know how to use the limit definition. All right. Let's start with the constant rule and the power rule. They're kind of, the constant rule is kind of a special case of the power rule. So what does the graph y equals 2 look like? And what is its rate of change between x equals 0 and x equals 3? I could have chosen any x values, but it's a constant function. And 1, 2, it looks like this. It's a horizontal line. So we have the point 0, 2, and we have the point 1, 2, 3, 2, y equals 2, x equals 0, x equals 3. Slope between x equals 0 and x equals 3 we can find by saying m equals y2 minus y1 over x2 minus x1. 0 over 3 is 0. And so the constant rule for differentiation says if c is a real number that's a constant, then the derivative with respect to x of that constant is 0. We see that the slope of a constant function is 0. That's y. So the derivative of any constant is 0, even if it's a constant like pi. So all of these here are all constants. Their derivative is going to be 0. And it doesn't matter what variable you're taking the derivative with respect to. When you see a constant, it doesn't have to be the derivative with respect to x. It could be the derivative with respect to any other variable in the problem. We'll start seeing that later. So the power rule for differentiation is if n is a non-negative integer, then the derivative with respect to x of x to the n, notice this x and this x match each other, is n times x to the n minus 1. It's important that we're taking derivative with respect to the variable that is the base here of this power function. And we are going to multiply by the exponent and then drop the exponent by 1. An integer is an element of the set. Capital Z here, it's kind of bolded. That's why we have that extra line, is to show that that's a bold. We can't bold our handwriting, so we put extra lines next to it. So it's not fractional. It's not a square root, something like that. It's the whole numbers and their opposites. So there's that whole set of what an integer is. And actually, even though we say it's a non-negative integer to start off with, actually, this is going to work for any real number. We just want to start off with easy examples. So let's see if we can start off with some simple examples here. So the derivative with respect to x of x squared is going to be 1 times 2 is 2. Drop that exponent by 1. It's going to be 1. Times 1 is 2. X to the first, that's going to be 2x. Now we have 44 times 1, x to the 44 minus 1, be 44, x to the 43rd power. Now let's think about this one. We have 1 times 1, x to the 1 minus 1 is going to be 1, x to the 0 is going to be 1 times 1 is 1. Recall that x to the 0 equals 1 as long as x is not equal to 0. And the derivative with respect to x of 2 to the 8th, don't get confused by that, even though that looks like it's going to be a power rule. This is really the derivative with respect to x of a number, 256. It's a constant, so that's just going to be 0. There were no x's, so there's an x to the 0 here, and 0 times anything is 0. All right, now we're going to talk about the constant multiple rule. You kind of saw me already incorporating that a little bit by saying multiply by the constant that's out front. The constant there was always 1. So when we take the derivative of c times f of x, we have the c can come through the differential operator and just as an observer that sits there, it stays multiplied. We take the derivative of the function and then we multiply it by that constant. So let's go ahead and see why that works because of limits. Remember that constants can pass through limits, so constants are going to be able to pass through the derivative operator, which is a big limit. If y equals c times f of x, let's apply the definition of the derivative to find f prime of x. So we'll just say y prime is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So that's going to be the same as the limit as h goes to 0 of, and we have c times f of x plus h minus c times f of x over h. That c is a constant multiplier. That's going to be c limit as h goes to 0 of c times f of x plus h minus f of x divided by h. And because of the property of limits, c can come out front because it doesn't contain an h. This is my definition of f prime of x. So that's c times f prime of x, like that. Y prime. All right, so this one here is going to be negative 7/8 times the derivative with respect to x of x to the 11th power. So negative 7/8 times 11 x to the 10th is going to be negative 77 over 8 x to the 10th. This is going to be equal to 2 times the derivative with respect to x of x. It's 2 times 1. It's going to be 2. We already took the derivative with respect to x earlier and found it to be 1. So that's a special rule. Now we have 16/3 times the derivative with respect to x of x to the 7th. It's going to be 16/3 times 7x to the 6th. And 642. 7 plus 4 is 11. And x to the 6th. All right, now for the sum difference rule. So remember that we had a rule for limits that said that the limit as x approaches c of f of x plus or minus g of x was equal to the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x, and that the limit of the sum was the sum of the limits Well, the same thing's going to happen here because derivatives are big summations. So the derivative of the sum is the sum of the derivatives. The derivative of the sum is the sum of the derivatives. And since differences are just special types of sums, or we're adding the opposite, it works for differences as well. So as we would expect from this limit operator, the derivative operator can kind of, quote, distribute over the sum or difference. And we get that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x is equal to f prime of x plus g prime of x. In the same way, the derivative of f of x minus g of x is equal to the derivative of f of x minus the derivative of g of x would be equal to f prime of x minus g prime of x. So, and it doesn't matter how many things are added or subtracted together. We show the rule with only two functions added or subtracted, but if I wanted to throw in additional functions and say f of x plus g of x plus h of x, or have some combination of sums and differences, the same rule applies. So this is really going to be a rule that works with polynomials well, because we have a whole bunch of little power functions here that are all added and subtracted together. So note here, just before we even get there, the derivative of a product is not the product of the derivatives. That is not a property that is inherited from limits. So we'll need a special rule for that when we get to the product rule later on in the notes. We will get there, but just I talked about so far inheritance of some properties from limits with the constant multiple rule, and the sum difference rule. That's kind of one of the places. I think those are all the ones that we stopped looking at inheritance from limits. So let's go ahead here and say that if we want to find f prime of x, that's going to be the derivative with respect to x of all of this stuff. And then we're going to take the derivative with respect to x of each individual term. Remember, terms are separated by plus and minus signs. Plus derivative with respect to x of 10x squared plus derivative with respect to x of negative 3x plus derivative with respect to x of 9. Okay. Sorry that I write so big and needed 2 lines there, but this is going to be 3 times 14 x to the 13th plus 6 times 10 x to the 9th plus 9x to the 8th minus 6 times 5 x to the 4th plus 10 times 2 x to the 1st minus 3 x to the 0 plus 0. This can be f prime of x is going to be 42 x to the 13th plus 60 x to the 9th plus 9 x to the 8th minus 30 x to the 4th plus 20x minus 3, and then plus 0 does nothing. Right? So now we're going to take the derivative of the natural exponential function e to the x, and you may get to this one a little bit later in the book. This stuff is in chapter 5, but we're going to go ahead and talk about it now, just because we're talking about derivatives. So let's go ahead and say this is the only function in math whose derivative is itself. That's why it's a special one. We just love it. I say it's mathemagical. So if you want to have some fun here, prove to yourself here that the limit, actually, let's just do this one. Okay. And so if we tried to do this right now, we would see that this would be e to the 0 is 1. With exponent rules, 1 minus 1 is 0 divided by 0 like that. We wouldn't be able to do anything. So we would try, well, we can't do any factoring. Do we know any special rules we might be able to use to help us? And we might here, I'd actually just want to leave this for later in chapter 5. Let's leave that for chapter 5. So because we're going to need to talk about why we would want to do a different technique there than we've ever done before. So let's not do this right now. But do know that the derivative of e to the x is e to the x. And the answer to why that answer was 1 is because e to the 0 is 1. And so because e to the 0 is 1, that means that the slope of the curve at x equals 0 is 1 because of the definition of the derivative. So just tell you that that's what was going on with that exercise. All right, so 2 times the derivative with respect to x of e to the x is equal to 2 e to the x, and nothing changed. This is going to be 16 times the derivative with respect to x of e to the x plus the derivative with respect to x of 9 is going to be 16 e to the x plus 0 is 16 e to the x. So the exponential function is the fastest growing function we know about right now. The only way to make it grow faster is to make the base bigger right now. So while e is 2.71 something something something, I would have a faster growing exponential function if it was 3 to the x. Let's say that would grow faster than e to the x. But in general, exponential functions are the fastest growing functions that we know about. So don't forget with laws of exponents here for this problem that this is the same thing as the derivative with respect to x of 3e to the x plus 16x squared plus 12x to the negative second. And we're going to show you that that power rule doesn't have to be used only with positive integers. We can use it with any real number here. So this is going to be the derivative with respect to x of 3e to the x plus the derivative with respect to x of 16x squared plus the derivative with respect to x of 12x to the negative second, which is going to be 3 times the derivative with respect to x of e to the x plus 16 derivative with respect to x of x to the second plus derivative plus 12 times the derivative with respect to x of x to the negative second. It's going to give me 3e to the x plus 16 times 2x plus 12 times negative 2. X to the negative 2 minus 1 is a negative 3. So 3x, 3e to the x plus 32x minus 24 over x to the third. Now we're going to talk about higher order derivatives, and that's going to be something where we take the derivative of a derivative, let's say. So higher order derivatives, assuming y equals f of x, can be differentiated as often as necessary. The second derivative of f is f double prime of x equals the derivative with respect to x of the first derivative of f with respect to x. For integers n greater than or equal to 1, the nth derivative of f is denoted as f, and then in parentheses a number here that shows us how many times we're taking the derivative of f with respect to x. So, and we're going to say that that means that that's the derivative of the n minus 1th derivative here, and so on. So just some other notation to let you know about here that I didn't talk about before. In addition to prime notation, there's also this dot notation that we'll use later in classes like differential equations, and it's important for higher order derivatives like this, where if you see that, that's the same thing as this. And if you see this, that can be written with 2 dots, so on. It's just easier to see the dots and to count them than it is to see the tick marks and count them. The tick marks all kind of run together. Another thing that we're going to do sometimes, instead of with these primes will kind of are meant to look like Roman numerals, is where that comes from. So if we want the fourth derivative, every once in a while, we're going to use small Roman numerals like that, and you need to know that that's the number 4. So just some additional notations that you might see, that if you see anything that is a small Roman numeral in the exponent spot of your dependent variable, that's a derivative like that. And serves the same purpose as this. Sometimes we'll use the Roman numerals up there like that. Other times we use the dot notation. So I just wanted you to be aware, like this is the fourth derivative here, and this is the second derivative. I could have the third derivative. We kind of stop using prime notation with the third derivative. It's okay for a third derivative to do f triple prime of x, but after that we start losing track of the tick marks that are up there, the primes. So we would want, with the fourth derivative, would definitely be where we would start using this notation here. Don't use this prime notation after 3. Either use dot notation, and even that gets a little dicey after 3, or use the Roman numerals, or use the what looks like the power in parentheses that tells you the order of that derivative. Okay, so continue differentiating f of x equals x to the 6th minus 3x to the 5th plus x to the 3rd plus 4x squared minus 9 until you obtain a zero derivative. Make a prediction about how many derivatives you will be required. So I think that if I take 6 derivatives, I'm going to get to a constant here because the highest power here is 6. So I think I need to take 7 derivatives to ensure that it's a 0. I might get a 0 on the 6th derivative, probably not. I'm probably going to need 7 derivatives. So let's see here. My first derivative here is going to be f prime of x is going to be equal to 6x to the 5th minus 15x to the 4th plus 3x squared plus 8x, and then that constant drops off. Then second derivative is going to be 30x to the 4th minus 60x to the 3rd plus 6x plus 8. Third derivative is going to be 120x to the 3rd minus 180x plus 6, and that constant drops off. Now we've got our fourth derivative is going to be 360x to the 2nd minus 180, and that constant drops off. Our fifth derivative is going to be 720x, and that constant drops off. Our sixth derivative is going to be 720, and our seventh derivative is going to be 0. So we're going to take the n+1 derivative to ensure of a polynomial here to ensure that we get a constant, the n+1 derivative of a polynomial will be 0. Okay. Let's move on here to slopes of tangent lines. Let's write an equation for the tangent line to the graph. F of x is equal to 2x minus e to the x over 2 at the point 0, -1/2, and find all points on the graph of f at which the tangent line is horizontal. So f prime of x is going to be equal to 2 minus 1/2 e to the x, like that. When we go ahead and we stick 0 in for the derivative, we get 2 minus 1/2 times e to the 0 is 2 minus 1/2 times 1. 2 over 1 is the same as 4 over 2 minus 1 over 2. That's going to give me 3/2 for my slope. And I have the slope is 3/2, and I have my x1, y1 is given to me as 0, -1/2. And so I'm going to use my point slope form y minus y1 is equal to m times quantity x minus x1. That's a y-intercept, so I actually can just go ahead here and use y equals mx plus b instead. Y equals mx plus b. So let's find all the points on the graph of f for which the tangent line is horizontal for the last example. So f prime of x was equal to 2 minus 1/2 e to the x. We want to set that equal to 0. Where is -1/2 e to the x equal to -2? Let's multiply both sides by -2. E to the x is equal to 4. Take the natural log of both sides. X is equal to natural log of 4, which is the same thing as natural log of 2 squared is 2 times the natural log of 2. and x is approximately equal to, you can use your calculator here, 1.386. So somewhere right around x's 1.386, we'll have a horizontal tangent line. We will have a horizontal tangent line at x equals ln of 4 equals to ln of 2. Either way that you put that into your calculator, it's exactly equal to that, which is approximately 1.386. All right. For what values of x does the function f of x equals 2x cubed minus 5x squared plus 24x have a tangent line to the graph of x with a slope of 6? Let's find out. F prime of x is equal to 2 times 3 is 6, x squared minus 10x plus 24. We want to set that equal to 6. Let's go ahead and bring the 6 over and make this a function that's set equal to 0. Factor this 6 out. And we'll use the this should have been an A10. That's my bad. This would have been 2 times 3x squared minus 5x plus 9. That looks better to me. See if we can factor this. Not sure we can. If we can't, then we're going to use the quadratic formula. Signs are the same. They're both negative. Let's see. 1 and 9, no. 3 and 3, no. So it's time for the quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. We already got a problem because I see that that's 27 times something is bigger than this. There's no real solution to this. So that tells me that this graph here is never going to have an x value where the slope is equal to positive 6. So that's what this tells me. All right, so there will be no point on f of x where f prime of x equals 6 ever. All right, that's it for this video, and we will come back next time and we will talk about the product and quotient rules. We made an allusion to that about what happens when we multiply functions. We'll come back and talk about that next time.